How is a quantum state represented mathematically? Have you ever wondered how scientists describe the strange and fascinating world of quantum mechanics? One of the key concepts is the quantum state, and it has a unique mathematical representation. Let's break it down in a way that's easy to grasp. A quantum state is represented as a vector in a complex Hilbert space. This is an abstract space that can have different dimensions depending on the system being studied. The state vector is often shown using Dirac's Braket notation, which looks like this: psi. For a single particle moving in one dimension, the quantum state can be expressed using a wave function, denoted as psi xt. This wave function is a complex-valued function that depends on both position x and time t. It tells us how the quantum state projects onto the position basis, which means we can write it as psi xt is equal to x psi t. Now here's where it gets interesting. The square of the wave function's magnitude, psi xt2, gives us the probability density. This tells us the likelihood of finding the particle at a specific position at a certain time t. To make sure our probabilities make sense, the wave function must be normalized, meaning that the total probability across all space equals 1. In a broader sense, the quantum state vector psi can be expressed as a linear combination of basis vectors. This is known as superposition. For example, in a two-level system, like a particle with spin, the state can be represented as psi is equal to alpha up, beta down. Here, alpha and beta are complex coefficients that must satisfy the condition alpha 2 plus beta 2 is equal to 1. When we deal with systems made up of multiple parts, the overall state space is formed by taking the tensor product of the individual Hilbert spaces. This means that the states can either be separable, which can be expressed as a product of subsystem states, or entangled, which cannot be factored in that way. Entanglement is a vital aspect of quantum technology, especially in fields like quantum computing and quantum communication. Physical observables such as position, momentum, or spin are represented by operators that act on these state vectors. The evolution of the quantum state over time is governed by the Schrödinger equation. The Hamiltonian operator, which represents energy, plays a crucial role in determining how the state changes. To sum it up, the mathematical representation of a quantum state involves a complex Hilbert space, state vectors, wave functions, the principle of superposition, tensor product structures for composite systems, and operators that representing measurable quantities. Understanding these concepts is essential for anyone interested in the exciting field of quantum technology.